Hello, I'm Wei Kang from U.S. Naval Postgraduate School. Before I start the technical part of my presentation, I would like to thank the organizers for this opportunity of giving a presentation in this symposium on machine learning and dynamic systems. In this difficult time of pandemic, organizing anything is difficult, so their effort is greatly appreciated. Okay, so let me share the screen so that you can see the slides of my talk. So the title of my talk is Data Generation for Deep Learning in Model-Based Optimal Feedback Design. This is joint work with a group of people, including Qi Gong from UC Santa Cruz, Fariba Farouk from US Air Force Office of Scientific Research, and Tanavi and Evan are graduate students at UC Santa Cruz. So basically, today the focus of my talk is about control system, especially feedback control for the purpose of minimizing a cost or optimal control. Control theory has been studied for many, many years, and a lot of great results have been found since the patriotic time, or that you see a lot of things related to the optimal control in the traditional sense, but then I will talk about the machine learning at the same time. So in control theory, most of design, I say they are model-based. Basically, the control theory is based on a model, which we assume is reasonably reliable. And then we design controllers so that the control system can do something. The nice part of a model-based design is that it has guaranteed performance. It has guaranteed performance. For example, if you follow the design methodologies in control theory and then you do it right, then you can guarantee that the system will be stable, for example. Or you can guarantee that the system will be driven so that a performance cost function is minimized, right? That's optimal control. Or you can control the bound of the gain between the noise to the performance, right? So there are all kinds of different control goal you want to achieve, and the control theory can give you a guaranteed performance. That's great. But then the model-based design has one bottleneck. One bottleneck is cursive dimensionality, because many of these designs require the designer to solve some kind of PDEs, for example. And if you use traditional way of solving these PDEs, the complexity of the problem increases exponentially with the dimension. So basically, if you try to solve a problem beyond 4 or 5 dimensions, that becomes very difficult, if not impossible. All right, so that's cursive dimensionality. On the other hand, machine learning has been actively developed for many years too, and with many successful applications. And it has a reputation of dealing with high-dimensional data. Dealing with high-dimensional data, that is great, so that may give us hope to overcome the curse of dimensionality. However, guaranteed performance like convergence or stuff like that, or stability, it's not always so easy in the machine learning approach. So you need to validate the solution, okay, to make sure it can be generalized outside the training data. Anyway, so the idea is that can we combine these two, okay, so that we can take advantage of machine learning to actually overcome the curse of dimensionality. At the same time, we take advantage of also the model-based design so that we can guarantee performance. Okay, so more specifically today, I'm going to talk about some work we have been done lately. We call it the data-driven in model-based design. Okay, you still do model-based design. However, inside this design, some part of design, when you face a curse of dimensionality, we take the approach of data-driven approach. More specifically here, in this particular work I'm going to talk about, we use machine learning okay, in the data-driven approach. Then we see that the model-based design, it not only helps us to guarantee performance, it actually, we can use a model to generate data. Okay, you can, so the data you can generate at any location you want. So that's good. Another advantage of using model-based design is that the model is there. You can use that to validate the performance actually. So that's good too, especially when you talk about machine learning. So you have effective way to validate the solution. That would be great. And then, of course, then machine learning is a part we use to overcome recursive dimensionality. So that's kind of a philosophy we're trying to follow. And more specifically, the first part of my talk will mostly come from this paper, okay? So for those who may not be that familiar with optimal control, this is a fairly standard family of optimal control problem, where you have the control system is defined by an ordinary differential equation. Then the X is the state of the control system, and U is a control. You can adjust or determine the value, and then you drive the system. You drive the X to do something. The initial state, it does not have to be fixed, all right? Then the goal here is to find a feedback law for closed loop control. Now, what does that mean? For those who are familiar with control system, I don't have to explain, but just in case if you're not so familiar with control system, in control theory, there are two kinds of control functions, okay? One is a feedback law like this. It's a function of time and X. That means in real time, your sensor tells you, or your sensor with your estimation system, you tell you what is X, your state at this moment. Then you real time compute the control value at this moment. Next time moment when X changed, the sensor will tell you where is the new X, then you adjust that, use a new value of U. So that's feedback law that you can use for real time. Open loop is another thing that is a control that the control function has no X, just T. So basically the control profile is a function of time. Okay, it doesn't adjust with your current state. Okay, so one way to think of that is, let's say, if you shoot a rifle, you aim the target, then you think you're pretty, aimed very well. Now you pull the trigger. Then after you pull the trigger, you have no control. Okay, just hope that you can hit the target. So that is open loop control. Okay, so once the process starts, you don't have way to adjust. Your control is fixed at any time. T is fixed without X. Now feedback control is like you launch a missile. Okay, after launch, the missile sensor constantly or update the state of the target and your current state, and then you, based on that information, you real time do the adjustment. Okay, so in general, feedback control is harder than open loop control design. So we do have ways to compute open loop control, but to make the closed loop, it's another thing. It's much more difficult. So we'll get into more about open loop and closed loop later in the talk, but basically that's the idea. Okay. Then when you have this control problem, you want to find a closed loop control law. One way to do that is to use HJB equation, Hamilton-Jacobi-Bellman's equation. The idea is that you form this Hamiltonian function. Here, this is a running cost. Basic running cost is a cost here. Then you accumulate that and plus terminal cost. The goal of the control is to minimize this cost. That's the optimal control goal. You want to find this closed loop feedback law to minimize this cost. Now the approach is to form this Hamiltonian functions. Lambda is called co-state here, okay? It's kind of like the multiplier, but yeah, it is multiplier, but that's what we call it co-state in control theory. And then to solve this PDE, okay, this Hamilton-Jacobi-Bellman's equation, if you can solve it, then the solution V represents the optimal cost. We call it value function. And this value function, you take the gradient, you plug into this minimization. The assumption is that the minimization of the homogeneous is not too hard. You can do it real time. For many problems, you can design, if your design is has some kind of good structure, you can even write down the explicit solution minimization. But anyway, we assume that this minimization is not too hard. Then you can real-time compute this one to do this feedback control. Okay, so then it guaranteed that cost function is minimized. So that's good, right? However, the curse of dimensionality comes here because this equation, look at this equation, the space dimension, time is one dimension, but then the space dimension of this PDE is the same as the dimension of the state space of the ODE. Okay, when you design the mechanical system, this dimension can easily go to 6, 7, 12, 20, easy, okay? So now imagine all of a sudden you need to solve a PDE with that kind of dimension. Of course, I mean, in general, it's just impossible using traditional numerical PDE, right? So that's where the, if you use grade, for example, to solve the, you use grade like finite difference or central difference, then the size of the grade increases exponentially with the dimension. So that's pretty soon you run out of memory. So anyway, that's not the best way to approach it, if the dimension is high. Then here, the data-driven in model-based design, in the paper I mentioned earlier, we use this following approach of adaptive learning. Then we use neural network to approximate the value function. Okay, remember, if you have the value function, you plug into this formula, you got the feedback control, everything will be good. Now, the difficult part is to find the value function, right? You need to solve HJB. So that's a part we try to replace by this solution of HJB, we replace it by a neural network. Okay, maybe it's more, visual. I mean, let's explain this idea using this flow chart. So you have a control system. Well, this system is slightly more complicated than the one I showed you earlier, but let's don't be bothered about that. Then you have the model, basically, okay? Then you start to generate data, and so that you can use the data to train the neural network. The data means that you find randomly a lot of points of X. Then you compute the value of V. Then you say, wait a second, how can you compute that? Okay, that's something we use open computational optimal control to find open loop control. I will get back to this topic in the second part of the talk. So right now, let's just assume we have a way to compute V at an individual X, not as a function, but at individual X, we can compute V. Let's just make that assumption. I'll get back to that point later, okay? Now, suppose you can find the data, the value function at individual points, then you can generate a lot of data. Then you do the neural network training to train a neural network that we call VNN, the neural network approximation of V, okay, as a function. And then once you train that, then actually you can generate data for the validation, because you have the models. Model is in your hands, that's great. You can generate the data for not only training the neural network, but also validate the solution. And then when you validate the solution, if the error is something, too large, you are not happy about that. And then, there are a convergence issue, we'll talk more later, but basically say, okay, let's generate more data, okay? And then you do the training again. And then you test the error again. If it's not accurate enough, you generate more data. So it's adaptive sampling using the model. Then until, at the point where you're happy with the error, then say, okay, then here is the control law. You have the feedback control law. You can plug into the system and start to operate. And then the control law looks like this. Of course, I mentioned that before, except that here I don't know the value function, but I use a neural network to approximate that function. All right, and I hope that this neural network can give us an approximate solution of V when X has higher dimension. Okay, so that is the technical, say, outline of approach. Now let me explain this idea using example. supposedly we want to stabilize a rigid body satellite, to point to certain fixed orientation. So I want to drive, so the state is the Euler angle and then the angular velocity. So there are 6 dimensions. I want to drive them to 0. Say, that's my ideal attitude. That's my ideal angular velocity. I want to point this to and stabilize around a desired orientation. Okay, so now there are, that's all standard formulation of rigid body dynamics, everything. But by the way, here we're not using thrusters. We assume the control is momentum wheel, so make a little bit more nonlinearity into the dynamics. But anyway, that's all standard, So, and then we have this quadratic cost function where basically I want to minimize this cost, means that I want the final state, final Euler angle and the final angular velocity, they all become 0, and that's the weight we choose. Okay, so that's a 6 dimension in space and 1 dimension in time, and then solve that PD. Of course, it's a very, very difficult, and we don't have an analytical solution for this problem. Okay, and then what we do once again, just we would come back to this, how to generate the value at the individual point later. Say, suppose we have a way to compute the value function. So you randomly generate some, initial condition. Then you can compute the value function. And you can compute something called co-state, okay? The co-state actually is from the Pontryagin maximal principle that gives you the gradient information of the V, which we need for the optimal control, right? So once again, we'll talk more about that, but basically here, I want to explain from this page, what you need to see is, to focus is this loss function. Here, so you have a whole bunch of points, okay? Then the value function at the point. So you use your neural network to compute this value. So that's the supervised learning, okay? And the gradient at this point. So you compute the gradient, which is actually pretty cheap when you compute the gradient of a neural network. Then you compare to the co-state. Then you put the weight to balance between these two, which part you want to weight more. And then you minimize this one to train your neural network. Okay, then we start from 64 points and we increase in adaptive sampling, which that's what we do. But anyway, so at each step we try to minimize this loss function. Then the domain of control, we assume that my Euler angle can be positive, negative 60 degree with a positive power of 40, power 4 and positive power 4 per second of angular rate. That's a region, and now we want to find optimal control within this region. Okay, then so we use this 64 neuron each layer, and then 3-layer neural network, and the activation function is a hyperbolic tangent. While in this problem we use moving horizon control, so I only need the approximation of the value function when time is 0. There's some detail about control theory, moving horizon. Let's skip that. But basic idea, I'm approximating a solution of HAB equation with 6 state variables. And there are, cold start, warm start, which I will talk about later. But anyway, we generate data and then we do the training. We found that if we generate to 8,000 grid points, then the relative error will go down to the range of about negative 10 to negative 3, 10 to negative 2 level, and that is that. Now this dotted curve is compared to an old paper I wrote several years ago. We used sparse grade to solve this problem, and so that's an error over there. So we use that as a comparison standard. So after 8,000 grid point, sampling point, we beat that result. And in this result, for the sparse grid, I need more than 44,000 grid points to solve this problem with this accuracy. Okay, but actually we can do things a little bit better. Okay, then the idea is that when you do the sampling, there's some location where the surface of the solution is flat. When it's flat, you don't need actually many sampling points. So the region where the surface actually change very fast, that's where you need more grid point, right? So once you have the sampling, you can approximate, you already have, if you have a first neural network, and then you're not happy with that, right? And then what you do is that you can compute its gradient and see where you have large gradient. Then you generate more data around the area where you have large gradient, right? So you target regions where it's difficult to approximate. Then you generate more data. So that's adaptive sampling. Okay, the basic idea. There are details, how many points you need to generate, everything. You can go back to that paper. It has more details about the data size you need. But anyway, here's another simulation. Rather than generate 8,000 grid point at the same time, actually, we start from just 64 points. And then we're not happy with this relative error. Then we generate more and more. So actually, by only 4,000 grid point, we can even beat the 8,000 grid point case. Definitely beat the sparse grid case. We get a smaller error with a smaller number of grid points. So that is, well, the mu is, remember we in the last function, we have two parts. One part is the value, will compare the value of function. One part will compare the let's say the gradient and the closed state, right? So that's the, depend on what is the weight you put, the result is different. So you have to try something. And then for the ideal case of mu, then you get something like this, okay? So that's, once you have this value function found and you're happy with the error, then you can plug in the formula of optimal feedback control law in the Pontryagin maximal principle. Then you can actually, close the loop, and that's one example of a typical trajectory where you can stabilize the angular velocity and the Euler angle. Okay, so that's the a example that illustrate how we solve the relatively high dimensional optimal control problems using data-driven in a model-based design. Now, from the example, it is clear that data is essential. Okay, so I told you earlier that let's assume we can generate data. Then the question is still there. How do we generate data? We need the data to train the neural network. We need the data to validate the neural network. We need more data at the targeted region to do the adaptive sampling, right? All these need a fairly effective way of generating data, okay? So how to do that? Now here is a question. Now in the next part of the talk, I'm going to review a set of methodologies that you can use to generate data. But before I start, it's not really, I will probably get into a little bit more details in one or two methods, then I will give some other method without much detail. But anyway, before I start the technical detail, there's one thing I want to emphasize. What kind of algorithm that you can use to generate data? What is a good algorithm you want to use to generate data for this kind of data-driven in model-based design? I would say causality-free is a very important property, okay? By causality-free, I mean that the computation of a value function at a point is computed without using the value of v at any other point. For example, any finite difference or finite central difference or finite element type of approach is not causality-free because you need a structure of elements or grid points. You swap the region, so the computation of one point it depends on the neighborhood value of the function. That's not causality-free. Okay, so we want causality-free this property, because if it's causality-free, because it does not depend on the grade. So you have the opportunity or possibility to push the idea to a higher dimension, because as I said, that the grid size increase with the dimension exponentially. So if anything depends on grade, then you cannot go to high dimension, okay? So causality-free doesn't depend on grade, so you may solve a high dimensional problem. And causality-free is convenient for generating data in targeted region. Because it's causality-free, you don't have to swap the whole region. You can focus on any region you want, and that make your data more efficient. Okay, so that's for adaptive sampling, as I showed you in the example. That's exactly what we did. So we want causality-free so that we can target at any region I need. Okay, then you know, for HJB equation, actually sometimes the solution has a non-smoothness, okay? And around those points, the solution is not accurate as maybe some other points, right? So because it's causality-free, the error is controlled point by point, so it does not propagate to nearby points. So that's good to control the error. And also, many actually causality-free algorithm has estimation error. That's great, because as you know, as we know that for machine learning, sometimes we don't have guaranteed error, you know, for many cases. So here, if you have error estimation, it can give you a, you know, reliable way of providing error analysis. I think that's great. And another thing is causality-free is that it's perfect, you know, it has perfect parallelism. I mean, it's embarrassingly parallel. Basically, you know, you can fire up hundreds or thousands of CPUs to compute at different locations, because each point is computed independent from other points. So you can compute them separately in different CPUs or different processors. So in the sparse grid paper that I mentioned before, we actually fire up, you know, more than 500 CPUs, just, you know, compute the 44,000 grid points. So that's parallel property is good. Then of course we use this data to for the data-driven approach. So that's why causality-free is important. Okay, and then in this paper, we actually surveyed a list of causality-free methods. I don't have time to go through all this method, but let me go through one or two of those that I'm most familiar with. Those are the ones we used before, but then I will mention others. Okay, so we categorize them into characteristic method-based and direct method, minimization-based method, and a stochastic process related algorithm. Okay, so let's see what is characteristic method. Okay, let's start from the first group. Once again, here is a optimal control problem. Now this time to generate data, we don't know, you know, we use an open loop solution to generate data actually, so that we can train the neural network for the closed loop feedback controller. So here I just need a solution with dependent on time. Assume everything's perfect, and then give me any grid point. I want causality-free, right? So you give me any, not grid point, any point, sampling point. I want to find optimal control, okay, to minimize the cost. That's open loop, okay? How to do that? I mentioned several times already, Poincare maximal principle. It's actually, you still form a Hamiltonian, like the HJB equation part I talked before, but this time you form a Hamilton dynamics. Then the co-state and the original state, the primary state, they both satisfy ODE, a system ODEs. It's 2-point boundary value problem. Okay, at the initial time, you know your state, that's your initial state, the sampling point. Okay, then at the terminal time, you know a relationship of the co-state, okay, with the terminal cost, and that's a value function. So that's an ODE that you solve. If you can solve this 2-point boundary value problem, and then you find optimal control by plugging into the formula, and you find this open loop control. Okay, so that's, and actually the Poincare maximum principle in this, the Hamilton dynamics in the PMP is a characteristic. So anything related to solving the system we call characteristic methods. Okay, and you know, this is 2-point boundary value problem, and we know that you know, in numerical analysis, a lot of people will tell you two-point boundary value problem is bad. It has a bad reputation because it diverges. It can easily diverge when you do, like shooting. It's really unstable, right? Actually, this method, it turns out that it's all dependent on initial guess. Okay, if you have a good initial guess, this problem can be solvable. Okay, so it's all about how to do the initial guess. Okay, so one way to do that is called type matching. Say at the beginning, you have no idea what is good initial guess, what you can do. And you want to find optimal control from T0 to Tk, for example, it's long interval. However, you know that if a T1 is a small interval, it's very close to 0. In the extreme case, a T1 is T0. If T1 is T0, you already know the solution. Everything's constant. Okay, that's it. So you know a good initial guess. So suppose T1 is very small. Then you pretty much know a good initial guess. It's constant, okay? And then you can solve that boundary value problem. You got an optimal control, but you say, wait a second, it's not the optimal control you want because your true final time is here, right? That's fine. Let's extend this to a second small time interval where you use this one, you stretch the solution. This is not optimal anymore after you stretch, but it can serve as a reasonable initial guess. Then hopefully the second interval, it converges. Now you keep stretch it, and finally, hopefully you'll get here, okay? So that's called time marching, okay? And then how to stretch it, there are different ways. You can use step function, you can use linear, extension, whatever, but there are different ways to do that. However, the idea is that you use many small time intervals and do step by step, then finally you get a optimal control of this problem for the full time interval. Oh, by the way, I want to mention here is this Pontryagin maximal principle or the characteristic method does not guarantee you get global optimal. It does not even guarantee you get local optimal. Okay, so when you apply this method, you need some knowledge about optimal control so that you can reasonably believe that's at least a local optimal. So what you find can be local. Okay, so that there are more details here. I don't have time to cover, but the example like rigid body, we know it's because it's quadratic cos. We know locally it has a global optimal. So that gave us the confidence using this method. But anyway, it's hard to guarantee it's a global minimal and even local minimal. So there are more things involved here. I don't want to say you solve this one guaranteed everything's optimal. No, but anyway, we don't have time to go on into all these, but some of these problems still need research. But anyway, suppose you get reasonably believe these solution are local minimal, then you can use the data to train the neural network. That's what we did for the rigid body problem. And then, the bottom line is that after I found the control, I can validate the value function. It's local minimal, global minimal, but as long as the cost is within your tolerance, say, okay, that's a cost I can pay, then that's good. Engineering-wise, it's a practically useful control already, right? So, but anyway, so the nice part about this type marching is that it does not need an initial guess. Your very initial guess is actually this small time interval. It's a constant. So pretty much you don't need any skills of doing initial guesses. So that's good. And this idea can be extended to space marching too, okay? And then it is causality-free. Okay, you stretch time, but the initial point is there. You can choose any initial point, then you start to stretch time, or even stretching in space. Initial condition does not depend on nearby solution. Okay, and then when solving this boundary value problem, in a lot of time we use a BVP, 5C, MATLAB, and recently we use a solver in Python as well, actually. But this method, in this paper, you can see that they have approximation of error. So that's good. We use that approximation to analyze the accuracy of a result. Is very useful, the error estimation. Then it can be, how to get a bigger initial Tom, if you have some local solution already for optimal control, for example, the Albrecht method, then you can problem has a big initial guess for a larger time interval, and then that can save your time. But the disadvantage of the method is that it can be slow. As you can see that, you have to do one interval, another interval, depending on how many intermediate intervals left. In the rigid body problem, it can be anywhere between 3 subintervals to 7. Okay, so it can be slow. Okay, so if it's too slow, what do we do? Well, another way we tried in the paper we recently published is neural network warm start. Okay, so now we even combine data-driven with the data generation. Okay, so what we do is that we generate a very small sampling solution for a very small sampling set, like 64 points only. Okay, then we do the learning. Then we approximate the value function. This is not an accurate approximation at all. Okay, it's a better approximation in terms of feedback control. However, it turns out that this approximation is good enough. You use a gradient, you can give an initial guess for the co-state. Then from there, you can give an initial guess for the primary state. Then all of a sudden you have initial guess, and it turns out this initial guess is fairly good. Okay, so the idea is that you use time marching to generate a first data to train a first inaccurate, not necessarily accurate neural network solution, but use that as initial guess to generate more data. It turns out that for that approach, you can get 100% convergence. Okay, if you want to get 100% or close to 100% convergence for the problem using time marching, it will be much slower. Okay, and then but using the neural network warm start, the convergence is much better, and then it's faster. Okay, so that's how we can generate adaptive data. So we have first data using time marching, then we have a first neural network, then we start to generate data at targeted region using adaptive sampling. It's really effective, actually. There's some other method, I don't get into detail, is also characteristic method. For example, the paper of ESO recently, that this paper actually, they use backward integration. Okay, you find one open loop optimal control, one of them. Then you start, for the closed loop, you start perturb at the final time, then you solve backward in time. You don't have a convergence issue. It always converge. The computation is very effective, okay, very fast. But you cannot exactly control the initial sampling point. It's because you integrate backward in time from TF backward to T0, so wherever you land, so it's a little bit difficult, or can be quite difficult if you want to do targeted region sampling, right? However, you don't worry about convergence. It's very fast, so there are advantage, disadvantage. Nevertheless, that's another way you can try. It's also based on characteristic. Okay. So now, characteristic method is good if the problem has no constraint. Sometimes the problem has constraint like this. Say, your state and control mixed together has to be bound by something. That's very usual for engineering problems, but numerically, it can be very difficult. It causes a lot of problems, non-smoothness, and the necessary condition, the punctuation maximum principle will become much more involved, and some for high dimensional problem even derive that necessary condition. So your characteristic will not be so. Problem will not be as simple as this one. Okay, so you have a transversality condition. It's not always easy to derive. So that causes a lot of problem in numerical optimal control. So there is another big family of open loop optimal control algorithm called direct method. Okay, there's a long list. Even this long list is far from a complete list. Okay, so it's incomplete list. All right. So, but the basic idea is that you discretize optimal control problem directly without using necessary condition or even Hamiltonian functions. You just discretize them, directly, then solve a finite dimensional optimization problems with nonlinear constraint. Okay, so let me show you a work, actually actively divided by Farouk and Mac Ross, and later Qigong and I did a lot of work with them as well on this called pseudospectral method. So in pseudospectral method, for example, you have, in addition to the standard, ODE control system, you may have constraint. It can be time dependent, but for the, it doesn't matter here. But anyway, so you have the constraint here, okay? And it's not even initial condition. You may have a combined of endpoint condition, okay? Not a simple initial condition problem. So that's how to solve this problem using direct method. In the pseudospectral method, in many direct method is that you actually find grid point in the time. One-dimensional time grid point is not increasing complexity. So that exponentially, so that's okay. Just one-dimensional grid points, that's okay. How to choose that? Different people use different approach. In pseudospectral method, we use things like, for example, one popular way we have been using in many papers is the Legendre-Gauss-Lombardo point. These points are very effective. Basically, it approximates function at high order, depend on smoothness. Okay, it has high order convergence. High order is very critical here because after discretization, the number of points directly translate into the dimension of a minimization. Okay, so basically the fewer number of points means that you do optimization later in the lower dimension space. That's very critical actually, right? So we want high order convergence here. And pseudospectral method is one way we can achieve high order. Now, once you have the grid point, then your cost function, this integral, the running cost and the integral is approximated by the summation with a weight function associated with a Gauss-Lombardo point. And then this ODE is approximated by this, this summation, this norm, and then with this differentiation matrix. Now, it's not equality here. Later, I'll briefly mention that it's associated to feasibility. You need to relax this constraint rather than zero, relax them a little bit in the numerical computation, okay? And then this other constraint are translated into discrete constraint directly, okay? Now, the next part of this approach is not only is a high order, and actually we can prove that if you discretize this one in this way, you can achieve, you can guarantee it's feasible. Okay, you have solution to satisfy all this constraint. And then now this problem is a constraint optimization problem in finite dimension. So you can use nonlinear programming to solve this. So you take advantage of the algorithm, in nonlinear programming developed for many, many years. So you take advantage of those algorithms to solve this problem. And then we can prove that if your discrete solution, when you increase the number of grid points, it approaches to a continuous function, then the continuous function must be the optimal control or it can be local, okay? Depend on what solution this nonlinear programming gave you, is a global or local, but it guarantees that the solution is consistent in the sense that if your discrete solution approach to a continuous time solution, that must be the optimal control of the continuous problem. Okay, so that's consistent. And actually for some family of optimal control, we can even prove that the convergence of this is guaranteed also. So that's one direct method. You can use that to handle it, especially useful when you have complicated constraints. Okay. Then there are other methods that are called the minimization-based method, led by a group of researchers like, Stan Osher and Darban, and then their teams. So for certain type of control systems, they can be fairly effective. They are causality-free, and there are other work actually. Wei Kang, I believe, is one of the organizers of this symposium, so I'm sure they'll present something. If you have a stochastic optimal control problem, then they are the first group that apply deep learning to solve these kind of optimal control problems using neural network. So that's another family of problems. You will see presentation on this approach. in this symposium. So I skip the detail, but basically here's the table. Once again, it's incomplete. Okay, there are many methods that you can use. They are causality-free. They can use to generate data. But I still gave you a table because I want to make one point I want to make is that look at this method. Some problems do not need initial guess, okay? Some need, but faster, okay? And then some has no initial, no worry about the convergence, but it's hard to control the initial condition, right? Some is more effective when you deal with constraints, some are not. Some can handle a system with stochastic factors in it. Some may be more efficient doing without, for system without stochastic uncertainties in the system, stuff like that. So basically the point I want to make is that number one, we don't have for optimal control, nonlinear optimal control with constraint or then even without constraint or with high dimension. So we don't have a silver bullet that kills all the problem. We don't have that. So it's good to have a toolbox of many different options you can choose. Really depend on the problem. You have to try probably more than one different algorithm to make it work. Okay, so it's good to have a book with toolbox, and then also, sometimes you may have one problem, multiple methods here can solve the same problem. That's okay. You have redundancy. That's okay. You can validate each other. So that's a so basically, optimal control, I think, is still a customized problem, the area that need customized design, okay? You gave a problem, you don't have, it's not like solving ODE, you have range kata, you pretty much solve most of the problem, reliably, but optimal control is not like that, so you still need to analyze a model, so model-based design is still valid, even if machine learning is very, very powerful, but I think we're not ready to just design optimal control based on data, based on neural network or machine learning without taking advantage of model. Model is still important here. You need analysis, you need customized design, and so a toolbox is very much important. That's a summary of the topics I talked about as conclusion, which I already emphasized multiple times in the talk, so I don't repeat them here. That concludes my talk, and thank you very much.